Clouds drifting across Hawaii's Big Island often reveal an immense landscape that challenges the imagination. Rising more than 13,000 feet, or about 4,169 meters above sea level, while extending far deeper beneath the Pacific Ocean, Mauna Loa dominates the island with a scale unmatched by any active volcano on Earth. Measured from its submarine base, the mountain towers more than 30,000 feet, or approximately 9,170 meters, making it one of the tallest mountains on the planet from base to summit. Its enormous mass covers roughly half of Hawaii Island, and its broad shield shape stretches across the horizon with slopes so gentle that the volcano can appear almost deceptively calm. Yet modern scientific instruments have detected something remarkable. Mauna Loa is growing ever so slightly larger, not because its rocky flanks are breaking apart into a catastrophic collapse, but because molten rock is quietly returning beneath the summit, slowly refilling the volcanic plumbing system left partially drained after its most recent eruption. The idea of an enormous volcano expanding naturally sounds unsettling. Satellite measurements, precision global positioning system stations, electronic tilt meters, and earthquake monitoring networks have all confirmed that the summit region continues to rise by tiny amounts. Headlines and social media posts often seize upon those measurements, transforming routine volcanic behavior into dramatic claims that the world's largest active volcano is cracking open. Such descriptions create an image of giant fissures tearing across the mountain, signaling an imminent catastrophe. The scientific evidence points toward a far different explanation, one that is no less fascinating simply because it is expected. Every volcano has its own rhythm. Some remain dormant for thousands of years before awakening. Others erupt frequently with little warning. Mauna Loa occupies a unique place among Earth's active volcanoes because it has experienced dozens of documented eruptions since written observations began in the early 19th century. Between eruptive periods, the mountain enters a quieter phase during which magma rising from deep within Earth's mantle gradually accumulates inside underground storage regions. As that molten rock returns, pressure slowly increases within the volcanic system. The surrounding rock responds by stretching almost imperceptibly, allowing the entire summit region to expand by amounts measurable only through highly sophisticated instruments. To the human eye, nothing appears to change. Visitors hiking across Mauna Loa's summit landscape would never notice the mountain becoming larger from one day to the next. The inflation occurs over months and years rather than minutes or hours. Individual measurements often involve movements smaller than the width of a fingernail. Yet when scientists compare continuous observations collected over long periods, the gradual expansion becomes unmistakable. Understanding why requires looking far below the lava fields that dominate the volcano's surface. Deep beneath Hawaii, an exceptionally hot plume of mantle material rises from hundreds of miles or hundreds of kilometers below Earth's crust. This mantle plume continuously generates magma through decompression melting as it approaches the surface. Unlike volcanoes situated along tectonic plate boundaries, Mauna Loa exists above this long-lived hotspot where the Pacific plate slowly moves northwestward while fresh magma continues rising from below. As magma ascends through the crust, it does not travel directly to the surface in one uninterrupted journey. Instead, much of it pauses inside reservoirs where molten rock collects. These storage regions behave somewhat like temporary holding chambers within a vast underground plumbing network. Pressure inside those reservoirs changes depending on how much magma enters, how much escapes, and how efficiently surrounding rocks accommodate the increased volume. During an eruption, enormous quantities of magma leave these underground reservoirs and travel toward eruptive vents. Lava fountains may reach hundreds of feet into the air, while rivers of molten rock race downslope toward lower elevations. The removal of magma decreases pressure within the storage system. In response, the summit often subsides slightly because less molten material remains beneath it to support the overlying rock. That process became especially evident during Mauna Loa's eruption during late 2022. Following decades of relative quiet, magma found pathways toward the surface, producing spectacular lava flows that advanced across the volcano's northeastern flank. Although the eruption attracted worldwide attention, scientists monitoring the event also focused on changes invisible to everyone watching glowing lava streams. Instruments detected shifts in ground deformation, reflecting the movement of magma through the volcano's interior. As molten rock departed the shallow reservoir feeding the eruption, portions of the summit experienced measurable deflation. Once eruptive activity ceased, another phase began almost immediately. The magma supply from deeper within the mantle did not stop simply because surface lava flows ended. Instead, molten rock gradually resumed moving upward through Mauna Loa's plumbing system, replenishing storage regions partially emptied during the eruption. This refilling process continues today and explains why scientists observe ongoing inflation. Inflation, in volcanic terms, does not mean the mountain is swelling like an inflated balloon ready to burst without warning. Rather, it reflects subtle changes in underground pressure distributed across an immense volcanic structure. Rocks surrounding magma reservoirs possess limited elasticity. Under increasing pressure, they deform slightly, producing minute upward and outward movement detectable by modern geodetic equipment. Global positioning system stations permanently installed across Mauna Loa provide one of the clearest windows into these changes. Each receiver continually communicates with satellites orbiting Earth, allowing scientists to determine its position with extraordinary precision. Differences measured over months reveal whether the ground has moved upward, downward, inward, or outward. These changes often amount to mere fractions of an inch, or only a few millimeters, yet they contain invaluable information about magma movement occurring several miles or several kilometers below the surface. Tiltmeters complement these observations by detecting tiny changes in the angle of Earth's surface. Imagine placing a perfectly balanced tray upon a table. If someone slips a thin sheet of paper beneath one corner, the angle changes almost imperceptibly. Tiltmeters measure similar shifts occurring naturally across volcanic landscapes. Rising magma gently alters surface geometry, producing signals far too subtle for people to notice directly. Satellite radar provides yet another perspective. Using repeated passes over the volcano, radar interferometry compares successive images of the landscape to identify minute elevation changes. Entire regions can be mapped with astonishing accuracy, allowing researchers to visualize patterns of inflation extending across the summit and upper flanks. Taken together, these independent techniques consistently indicate that Mauna Loa has continued inflating throughout 2023, 2024, 2025, and into 2026. The pattern closely matches expectations for a volcanic system gradually rebuilding pressure after an eruption. Rather than representing an unexpected development, the observations align with decades of previous monitoring conducted during earlier eruptive cycles. One source of misunderstanding comes from the volcano's extensive fracture systems, commonly called rift zones. Images showing long cracks across Mauna Loa often circulate online, accompanied by alarming captions suggesting that entirely new fractures are ripping the volcano apart. The reality is both more complex and far older. Mauna Loa possesses two major structural features, known as the Northeast Rift Zone and the Southwest Rift Zone. These elongated regions extend outward from the summit like giant arms reaching across the volcano's broad slopes. They formed over countless eruptions as repeated injections of magma stretched the volcanic edifice and established preferred pathways through which future magma commonly travels. These rift zones are permanent components of Mauna Loa's architecture. They have existed for thousands of years and represent areas where the volcano naturally accommodates internal stress. Lava eruptions frequently occur along them because ascending magma exploits these established weaknesses rather than creating entirely new routes through solid rock. Although surface fractures can appear within these zones during periods of volcanic unrest, their presence does not indicate that the volcano is suddenly splitting apart in a catastrophic manner. Instead, they reflect the ordinary mechanics of an active shield volcano, repeatedly expanding, contracting, and adjusting as magma migrates beneath its surface. The distinction is crucial because words such as cracking open often evoke images of structural failure. In reality, Mauna Loa has always contained these extensive fracture systems. Scientists monitor them carefully because they help identify where future eruptions may occur, not because they represent evidence of the mountain collapsing into separate pieces. The volcano's immense size also contributes to these natural deformation patterns. Mauna Loa contains an extraordinary volume of volcanic rock accumulated through hundreds of thousands of years of repeated eruptions. Every new lava flow adds additional weight. That enormous load slowly spreads outward under gravity, a process known as gravitational spreading. Rather than occurring abruptly, gravitational spreading unfolds over geological timescales. The volcano's flanks move outward by tiny increments as underlying volcanic deposits and ancient ocean sediments gradually deform beneath the mountain's tremendous mass. This movement interacts continuously with magma intrusion inside the rift zones, producing an ever-changing balance between internal pressure and gravitational forces. Scientists have spent decades untangling these overlapping processes because no single measurement tells the complete story. Inflation alone does not necessarily indicate an eruption is imminent. Likewise, earthquakes by themselves cannot predict exactly when magma might reach the surface. Only by combining deformation data, seismic observations, gas emissions, and direct field studies can researchers accurately evaluate the volcano's current condition. Earthquakes remain another closely watched indicator. Since the conclusion of the 2022 eruption, small earthquakes have continued beneath Mauna Loa's summit region and along portions of the upper southwest rift zone. These earthquakes often attract public attention whenever monitoring agencies publish updated seismic maps. Clusters of colorful dots can appear alarming without proper context. Most of these earthquakes are relatively small, occurring as rocks adjust to changing stresses produced by slowly moving magma. Some result from pressure building within underground reservoirs, while others reflect tiny movements along existing faults responding to gradual deformation. Such activity is entirely consistent with an active volcano undergoing post-eruptive recharge. Importantly, seismicity has remained within the range scientists expect for Mauna Loa during this phase of its volcanic cycle. Earthquake counts fluctuate naturally from week to week, with occasional swarms developing before subsiding once again. These variations provide researchers with valuable clues regarding underground processes, but do not automatically signal that an eruption is about to begin. The broad slopes of Mauna Loa appear remarkably smooth when viewed from the air, yet closer inspection reveals countless fractures crossing ancient lava flows, steep scarps cutting through hardened basalt, and long linear zones that have guided eruptions for thousands of years. To someone unfamiliar with the volcano's history, these features can look like evidence that the mountain is literally breaking apart. Photographs of open fissures are often shared online with captions claiming that enormous cracks are spreading across the volcano and that its collapse has already begun. The reality is far more complex and at the same time far more fascinating. Every active shield volcano grows through repeated injections of magma. Each time molten rock forces its way upward, it places surrounding rock under tremendous stress. Basalt is incredibly strong under compression, yet like any rock, it has limits. When pressure exceeds those limits, existing fractures may widen slightly, older cracks may reopen, and new, relatively small fractures may develop within areas already weakened by countless previous intrusions. These are not random tears appearing across an otherwise solid mountain. They are part of a geological system that has operated throughout Mauna Loa's existence. The most recognizable examples are the Northeast Rift Zone and the Southwest Rift Zone. These are not fresh cracks that suddenly appeared during recent years. They are ancient structural corridors extending outward from the summit, formed through thousands of repeated episodes in which magma pushed sideways instead of erupting immediately. Every intrusion stretched the volcanic edifice by tiny amounts. Over thousands of generations of eruptions, those repeated intrusions created broad zones of weakness where future magma would naturally travel. Scientists often compare these underground intrusions to repeatedly inserting thin wedges into the same piece of wood. One wedge produces only a slight separation. Remove it, and insert another in nearly the same place. Then repeat the process hundreds or even thousands of times. Eventually, the wood develops a preferred path where additional wedges slide in much more easily. Mauna Loa's rift zones formed through a similar process, except the wedges are vertical sheets of magma known as dikes that may extend several miles or several kilometers through the volcano's interior. When a dike forces its way into surrounding rock, it pushes the rock apart by small amounts. Sometimes that motion reaches the surface, producing narrow fissures or reopening older fractures already present within the rift zone. Those surface cracks often become the locations where lava eventually erupts if magma continues rising. If the intrusion stalls underground, the fractures may remain visible even though no eruption occurs. This process explains why photographs showing cracks on Mauna Loa's flanks can be misleading when removed from their geological context. Many of the fractures visible today have existed for decades, centuries, or even much longer. Some were created during previous eruptions. Others have been modified repeatedly by later episodes of volcanic inflation and deflation. They represent the accumulated history of countless eruptive cycles rather than evidence of an entirely new structural failure. The recent inflation detected across Mauna Loa does place additional stress on these established fracture systems. As magma gradually refills the shallow reservoir beneath the summit, pressure increases throughout the connected plumbing network. That pressure is transmitted into the rift zones, where surrounding rocks respond through extremely small amounts of elastic deformation. Existing cracks may widen by mere fractions of an inch or only a few millimeters, while remaining completely stable from a structural standpoint. Such minute changes can sound insignificant until one considers the remarkable sensitivity of modern monitoring equipment. Continuous global positioning system receivers can detect ground movements measured in millimeters. Satellite radar can identify subtle elevation changes spread across vast portions of the volcano. Instruments capable of measuring tiny shifts in Earth's surface reveal movements that would have remained completely invisible only a few decades ago. Consequently, reports describing the volcano as opening often stem from scientific measurements of deformation rather than dramatic visual changes visible to people standing on the mountain. Scientists may detect outward movement of the flanks amounting to only a very small distance over many months, yet those measurements provide crucial evidence that magma continues entering the volcanic system. Another important factor influencing cracks along Mauna Loa's flanks has nothing to do with freshly arriving magma. Gravity itself continuously acts upon the enormous weight of the volcano. Mauna Loa contains thousands of cubic miles, or thousands of cubic kilometers, of volcanic rock resting upon older volcanic deposits and ancient seafloor sediments. That tremendous mass slowly spreads outward under its own weight. This outward movement occurs extraordinarily slowly, measured in millimeters or centimeters over the course of a year, rather than dramatic shifts occurring overnight. Nevertheless, over centuries and millennia, gravitational spreading contributes significantly to the formation and evolution of fractures along the volcano's flanks. Existing cracks accommodate tiny amounts of movement, while new fractures occasionally develop where stress becomes concentrated. The interaction between magma pressure and gravitational spreading creates one of the defining characteristics of Hawaiian shield volcanoes. Neither process acts independently. Rising magma tends to force the volcano outward from within, while gravity continuously encourages the flanks to move downslope toward the surrounding ocean. The resulting balance produces an ever-changing pattern of stress that shapes the volcano throughout its lifetime. This is also where confusion frequently arises between Mauna Loa and neighboring Kilauea. Kilauea's southern flank includes the well-known Helena Slump, a massive section of the volcano that gradually moves seaward along a weak basal surface. That movement has generated spectacular coastal cliffs and numerous fractures over thousands of years. Because both volcanoes occupy the same island, reports about flank movement are sometimes mistakenly applied from one volcano to the other. Mauna Loa certainly experiences gravitational spreading, but its current inflation should not be interpreted as evidence that the volcano is beginning a massive collapse. Scientists distinguish between ordinary volcanic deformation and potentially hazardous structural instability by examining multiple independent datasets simultaneously. If the mountain were entering a period of dangerous flank failure, researchers would expect to observe widespread acceleration in ground movement, major changes in earthquake patterns, significant deformation across extensive portions of the volcano, and other measurable indicators occurring together. Instead, monitoring networks continue to record behavior consistent with post-eruptive recharge. Small earthquakes remain concentrated primarily beneath the summit and portions of the upper southwest rift zone. Ground deformation continues to indicate gradual inflation associated with magma replenishing the shallow storage system. Gas emissions fluctuate within expected ranges for an active volcano rebuilding pressure after an eruption. None of these observations, considered individually or collectively, indicate that Mauna Loa is undergoing an unexpected structural crisis. That does not mean the volcano is inactive. Quite the opposite. Mauna Loa remains one of Earth's most active volcanoes, and its history demonstrates that future eruptions are inevitable. The question has never been whether it will erupt again, but when sufficient magma accumulates to overcome the strength of the surrounding rock and create a pathway to the surface. Inflation is one of the signs that this long-term recharge continues, but it is only one piece of a much larger scientific picture. For volcanologists, the subtle widening of existing fractures along the flanks is valuable because it provides insight into the hidden movement of magma several miles or several kilometers below ground. Each tiny adjustment helps refine computer models describing the geometry of the magma reservoir, the orientation of underground dikes, and the evolving stress field inside the volcano. Information gathered during quiet periods becomes invaluable when unrest eventually accelerates, allowing scientists to recognize meaningful departures from normal behavior far more quickly than would otherwise be possible.